All right, so today we're going to focus on Darcy's law. And Darcy's law relates the flow of water out of kind of a package of rocks or sediments to the actual properties of those rocks and sediments that we're looking at. And we use it actually to calculate discharge in hydrogeology. So it's a fundamental law in hydrogeology. So let's go ahead and kind of jump into what that law looks like now. Essentially, the law is derived by Henry Darcy. He's a civil engineer in Dijon, France. And he published a book for the water supply of the town. And in that book in 1856, he and Charles Ritter had come up with a series of experiments that actually related water flow through a sandy column. And so here on the bottom right-hand side, you can see that sandy column. We have water flowing out of the bottom as a volume of water per time, which is our discharge, right? We can also think of that as a length cubed, so cubic meters per second over time coming out here. We have the column of that sand, and then there's a water being put in on the top to create some kind of hydrologic head in this system. Now that may change depending on the design, but that's what they used in this design experiment to kind of derive actually what is Darcy's law. So here's Darcy's law, again, is looking at Q, that flow or discharge in units of length cubed per time through a column of sand, or you can even think of it now when we discuss it as a volume of which we're looking through an aquifer system. And it's related to another term that we use, which is called volumetric flux. And the way these two terms are related is through the cross-sectional area. So here we have, in terms of this column, we can see at the bottom of the column, we're going to have this cross-sectional area. And when we divide the discharge by that cross-sectional area here, we end up with our volumetric flux. Now, this is in units of length per time, which looks a lot like a velocity, but is not a velocity term. And we'll touch on how you actually come up with groundwater velocities at the end of this lecture. So what Darcy showed in here is that our specific discharge flows in the direction of decreasing head, right? So we go from high head to low head. So if we go ahead and we draw a datum on here, we have our datum here. We have our, let's say, our head 1 here. We have our head 2 here. These are the two different pipes we're measuring it from. And we can see that the water level here is much higher, right? And so we have, let's say that this is going to be our elevational head, and this would be our pressure head here. And we can compare those in H1 and H2, and we see that water is flowing from a high head to a low head. We also see that Q is proportional to the differences in the head. So if we have a higher difference between our head 1 and our head 2, those two little columns or pipes pushed out, then we would have a higher Q. We would also find out that flux that Darcy, or that volumetric flux of water, is inversely proportional to the length if our change in head, right? If these columns stay the same, then it's inversely proportional to our L. Meaning that if our L gets longer, our Q would become smaller. If our L gets shorter, our Q would become greater. So Darcy's law is a fundamental relationship of flow and porous media. We can write it in a couple of different ways. It's an empirical law. It's based on experiments, right? And it is giving us a macroscopically average description of flow through billions of pores, right? So we're just kind of getting the average bulk of what's really taking place. And each of those different kinds of pores where this water is flowing, right, are much more complicated than what this relationship allows us to really describe. Instead, it really just gives us the bulk behavior of the system. So again, when you're working on your equation sheets, it's good to go ahead and say, okay, we have our volumetric flux. That volumetric flux is related to negative K over the change of head over the change in length. Another way to write that is that our volumetric flux is equal to the hydraulic conductivity of H2 where you measure it, so the head 2 where you measure it from the head 1. And here we're making like, let's say you have 2 wells in the ground, right? And you're always going to read your system from left to right. So this would be H1 and this would be H2. Okay. Divided by the length that's between those 2 wells. Or another way to write this is we could say, okay, the derivative of H over the derivative of the change in length. So in order to actually get the true velocity of which groundwater is moving, you actually have to take that volumetric flux or that specific discharge, and we have to divide it by the effective porosity. And the reason we have to do that is earlier we talked about this idea that effective porosity are the connected pores. And so it's only those connected pores that really can move the volume of water that's in your system. So we can say it's either that specific discharge divided by our effective porosity, or we can go ahead and we can say it is our hydraulic conductivity divided by our effective porosity multiplied by the change in head over the change in length. So what you're going to notice is that velocity is always larger than the volumetric flux. And the velocity is a rate of movement of a slug of water. So it's critical for predicting how solutes and contaminants move through the subsurface.